Good morning, I guess, everybody. I'm recording this on Saturday morning, February 19th. I promised yesterday in class, which was the last lecture that we had for 2002, that I'd do an example problem on mass moment of inertia. I'm going to share my screen now quickly, and we will talk about it. So here now you should all be able to see my screen, which is the writing pad, and I want to talk about the example problem from class. Here's the example problem that was given in the lecture notes. It was calculating the mass moment of inertia of this composite object. We've got kind of like 4 different objects that might be present in here, kind of this half circle, this full hollow circle, got this rectangular piece, and this triangular piece. And I was thinking a bit about this example problem, and I think it's a good problem generally, but it would require the use of some materials that you don't have on your equation sheet. So what do I mean by that? Well, you see that there's this triangular piece kind of on the lower left-hand side of this composite object. And I noticed that sort of the equation sheet that I put together for the class, I'll just bring that in here really quick, actually does not have sort of the triangular shape for mass moment of inertia of common objects. You could look this up on, let's say, Wikipedia or Google or whatever, this triangular shape and what the mass moment of inertia of that triangular shape is, but I would rather stick to an example where you can utilize some things from your equation sheet here. So instead of doing this example from the lecture notes with this object here, I thought about doing a different example. And specifically, I'm going to pick an example from a final of this class that I gave last year. So I'll pull up that other example problem now, and we'll work through that. I think it's a little bit more representative of an example problem that you might see on your final anyways. So let's get the figure in here, and then we'll talk about this particular example. So here is a sort of pendulum thing, and I'll bring in the text that goes with this particular example prompt. So here we've got slender rods in this pendulum apparatus shown. Each have a mass per unit length of 5 kilograms per meter. So we've got slender rod here and a slender rod here. We want to determine the mass moment of inertia of this apparatus about an axis passing through the page at point A. So here's point A here. And we want to know what the mass moment of inertia is about an axis that's sort of perpendicular to the page passing right through point A. So the beauty of making a recording is that you can pause the video right now if you want to sketch this object yourself, or if you want to copy the problem statement down, you can go ahead and do that. Otherwise, I'll assume that you'll have it done, and we'll just go ahead and get on with the problem. So the idea here is that we're looking at point A, and we're interested in an axis that passes right through that particular point. And we'll notice that we have 2 different slender rods here that are going to contribute to what is the composite body, right? So we have this particular slender rod, and we have this particular slender rod. And if you'll notice in your equation sheet for the class that mass moment of inertia of slender rods are given as Iy and Iz, which are axes that pass right through the slender rod, kind of in an axisymmetric way. So Iy and Iz are the same mass moment of inertia, and it's 1/12 ml squared. M is the mass of the object, and L is the total length of the rod. Okay. So we could think about putting that information in, is that generally for slender rod, I is equal to 1/12 ml squared. And specifically, this is the mass moment of inertia of an axis sort of passing through the center of the rod. So we have to remember that, like for this object here, that would be an axis passing through the center of this rod. And for this sort of object down here, it would be an axis passing through the center of this rod. Okay, so we have to keep that in mind when we're doing this. So maybe I'll put a coordinate system here, the typical XY coordinate system. And you might say in this case then that Iz is 1/12 ml squared for each one of these particular rods. And so let's then segregate this into 2 different objects. We'll call this object number 1, and we'll call this object number 2. And the basic idea is that each one of these objects has that mass moment of inertia, which is 1/12 ml squared, about its own individual centroid. And so we might label this as like G1, the center of gravity of object 1. And we might label this as like G2. And you could think of an axis that's passing through the page at these particular locations, which is running parallel to the axis that's passing through the page at point A, which is our general axis of interest. And so when you have this setup for these particular problems, you'll want to use the general equation for parallel axis theorem with composite objects. So in this case, we're going to utilize something like the mass moment of this object about an axis passing through A is what is the summation of the mass moment of inertia of each individual object. I think we label that as I tilde, I hat, plus MI DI squared, where remember this D is the distance between parallel axes of interest. Okay, let's get on with it. And let's sort of understand what's going on with each one of these individual objects first, and then we'll come back and plug them into this general expression. Okay, so let's just take a look at object 1. We know that for object 1, the mass moment of inertia of this object about an axis passing through its centroid is something like I tilde object 1, and maybe we want to label this as passing through the z-axis, right? So it's the z-axis sort of into and out of the page. Here's going to look something like 1, 12, m1, l1 squared. And now we get to a point where we're going to need to sort of figure out what the mass is for this first individual slender rod. So here's this first slender rod of interest, and we notice that it has a length of 200 millimeters. So that's useful because in the problem statement here, we're told that each of these objects has a mass per unit length of 5 kilograms per meter. Okay, so that's useful information. So since L1 equals 200 millimeters, and density per length is, sometimes you see this as like rho prime or rho double prime. This is equal to 5 kilograms per meter. Then we could say that the total mass of object 1 is something like 0.2 meters, which is the total length of object 1. I'm putting it here in meters, so this is just a direct conversion from L1, times the density per length, which is 5 kilograms per meter. And you'll end up here with the mass of object 1 just equal to 1 kilogram. All right, well, that's nice. So utilizing the density per length of this object in the calculation of the mass. So we're then ready to calculate this I tilde 1z. So here this is going to be 1/12. The mass of object 1 is 1 kilogram. The length of object 1 is 0.2 meters squared. All right, so if you work this out, you'll end up with a mass moment of inertia for the first slender rod, which is this vertical rod, about its own center of gravity, is going to be here 0.00333 kilograms meter squared. So this is the mass moment of inertia of this first object about its own center of gravity axis passing through G. That's about an axis that passes through point G1 in the Z direction. So I'll come back down here. Again, here's I tilde 1. So we have the mass of object 1. We have sort of I tilde 1 about Z. We're also going to need, if we look at our parallel axis theorem, this distance between our axis of interest, which is the axis passing through point A, and our centroidal axis, which is the axis that passes through point G1 into the page. So in the case of object 1, D1 is the distance between the axis that passes through this point and the axis that passes through this point. Well, it's pretty easy to see in this case that this is 100 millimeters. Okay. So in this case, D1, 100 millimeters, or we're going to work at meters, so 0.1. So there you go. There's D1. Now let's move on to object 2. All right, object 2 is the other slender member in this assembly, which is this sort of horizontal bar. And we notice that this particular rod also has the same total length as the other rod. So here's 200 millimeters total. So that's kind of a nice, convenient occurrence for us. But the same strategy remains, is that I want to determine what is the mass moment of inertia of this object about an axis that passes through point G2, and then use parallel axis theorem to relocate it to an axis passing through point A. So again, we're going to need something like I tilde C2, which again is going to have the same formula, 112 M2 L2 squared. Since this object has the same length as the first, it's going to have the same mass as the first. And since its length is the same, this ends up being the same mass moment of inertia as the first slender member that is that vertical slender member. So here again, this is going to be 0.00333 kilogram meter squared. Reminder that the mass of this object again is still L2 times this density per length, which again is 0.2 meters times the density per length, which is 5 kilograms per meter, or 1 kilogram. And then we have to still define our D2, which is the distance between the centroidal axis of that lower object and the axis passing through point A. So again, there's an axis passing here through point G2. And there's an axis of interest that we care about, which is the axis passing through point A. So pretty easy to see that the distance between those two axes that are passing into the page at A and at G2 is this distance here, which is 200 millimeters. So here, D2, Mighty Ducks, is 200 millimeters or 0.2 meters. So we're ready then to go with our full formula for the mass moment of inertia about an axis passing through the page at A. So here I'm going to call this IA or IAZ, since it's the Z direction that we're sort of passing through at point A. And again, reminder, this is your parallel axis theorem. So it's the mass moment of inertia of each individual object about its own Z axis through its centroid plus MI DI squared, where I is signifying object I in the assembly. So for object 1, we have I1Z is 0.00333 kilogram meter squared, plus the mass of object 1 is 1 kilogram, and the distance that the axis of object 1 about its centroid and away from point A, we've already sort of seen this, is this 100 millimeters or 0.1 meters. Again, it is this distance here that you see between the Z axes of point A and point G1. So 1 kilogram times 0.1 meters. Right? And this is for object 1. And we're going to add to that the contribution of object 2. It has the same mass moment of inertia about its own centroid as object 1. So again, 0.00333 kilogram meter squared, plus the mass of object 2 is 1 kilogram. And the distance that the centroidal axis of object 2 is away from point A is 0.2 meters. So this here is for object. All right, so this is our full formulation, and you can calculate, plug in for yourself, and you would find here that the total mass moment of inertia about point A, but an axis passing through the page, which is the z-axis, is 0.0, 5, 6, 7. I think that's a nice example, utilizing some information that you can get on your own equation sheet. So again, I wanted to stay away from sort of some strange, complicated shapes that aren't available on your equation sheet. And I'll do the same on the final as well. I'm not going to give you anything on the final that you're not going to have easy access to with your equation sheet. So that's the end of this example. Thanks for sticking with it. If you have any questions, again, I'll be in office hours every day this week at 11 o'clock. So hope to see some of you there if you have questions. So long for now. Ta-ta.